The barrier between risk analysis of sea level rise in Boston. Hello, my name is Jay,
My name is Pernell.
And my name is Sohan.
and this is our MTFC project. Since 1950, sea water levels in Boston have increased as much as 8 inches. The sharp increase is a direct result of climate change, caused mainly by greenhouse gas emissions, and has wait. Okay, wait. The barrier between risk analysis of sea level rise in Boston. Hello, my name is Jay,
My name is Pernell.
And my name is Sohan.
and this is our MTFC project. Since 1950, sea water levels in Boston have increased as much as 8 inches. This sharp increase is a direct result of climate change and an increasingly worrying threat to the well-being of life on Earth. Climate change, mainly caused by greenhouse gas emissions, has caused the melting of glaciers and ice caps, as well as the expansion of seawater as the Earth warms. The city of Boston, located on the Atlantic coast of the United States, is particularly vulnerable to sea level rise and its implications, such as property damage, wildlife endangerment, and in particular, flooding. According to the NOAA, the National Oceanographic and Atmospheric Administration, sea levels are expected to face a 0.6 to 1.1 foot increase by 2030 alone. If the recent sea level projections remain consistent, a large portion of the city itself will be at a high risk of leakage and complete submersion in the near future. There are already over 14,992 properties at risk of tidal flooding in Boston. Without intervention, the city of Boston can face massive problems financially and to its infrastructure.
When it comes to our data methodology, we decided to use a vast array of both data sources and data visualization strategies and techniques. Our data was mainly extracted from the National Oceanic and Atmospheric Administration, or the NOAA, and the Boston government, specifically the Massachusetts Department of Transportation, which provided a data set related to flooding in the city. Once we acquired these data sets, we proceeded with our data filtration and cleaning through the use of the Pandas library in Python. Using this library, we were able to filter out columns that did not pertain to our analysis and empty or non-available data values. This enhanced our graphing sequences later on in the project and proved to be a focal point in our data visualization in general. When it comes to our data visualization and modeling techniques, we relied on programming languages R and Python, and we used the geographical mapping software ESRI ArcGIS to utilize pre-existing layers to visualize the affected areas of concern in Boston. We decided to approach the mathematical modeling aspect of the project with two main focuses, one centered upon the general sea level rise, and the other centered on the mean higher high wave rise, or simply mean tidal wave length rise. For the general sea level rise, we utilized and extrapolated a quadratic regression model, and for the mean tidal wave projection, we forecasted an autoregressive integrated moving average, or ARIMA model. We also took the mean sea level differences from our target year, 2050, from the present day to keep record of numerical changes. It's imperative that we note that we kept 2050 our target due to its industry backing from the NOAA. The first model produced was through using the programming language R to create a quadratic regression model. We experimented with an array of different regression models, such as quartic and exponential, but we ran the risk of overfitting. So after careful comparison, we came to the quadratic regression model, which implied the strongest correlation as demonstrated by the observed R-squared value of 0.62. The image seen on this slide uses the quadratic equation produced by R to extrapolate the regression model to our target year, 2050. At the bottom of the slide, we have the actual regression model equation. The mean sea level differencing here was essentially found through taking the 2050 projection and subtracting it by the present day mean sea level. After performing this operation, we ended with a value of 0.2, signifying an 0.2 meter increase that can have both fatal and catastrophic effects on Boston. The second model we produced was in regards to the mean higher high waves, or mean tidal wavelength, and we decided to produce an ARIMA model through the use of Python, specifically the listed libraries. Pandas, alongside the other two Pythonic libraries listed on this slide, provide us with a means of data filtration, ARIMA-based framework, and finally, a mode of outputting the ARIMA model graphically. After taking out ARIMA model, that model data regarding the mean tidal wavelength from 2018, the year provided, we focused on three values, the P, D, and Q. P denotes the order of autoaggressive components, D represents the degree of differencing, and Q designates the order of the moving average component. With a P, D, and Q value of 3, 3, and 1, we were able to accomplish a more reasonable projection of the mean tidal wave situation in 2050 and observe a 0.2 meter increase in the mean tidal wavelength from 2018 to 2050. This increase causes the mean tidal wavelength value to surpass the 1.20 meter requirement set by the NOAA that classifies the value as a severe flooding statistic. In this scenario, a severe flood could diminish as much as $20 million of real estate value and will have a 1% chance of occurring annually in Boston by the year of 2050, leaving the government very vulnerable to liability costs. These floods would also have the potential to destroy as many as 16,000 homes, leaving Boston residents just as vulnerable to potential flood damage costs.
As for our risk analysis, we utilize geospatial mapping tools to accurately display our data in a meaningful way. Using ArcGIS, we were able to effectively overlay data gathered in the mathematical process and project it on a geographical map of Boston. In this geospatial map, we define areas in blue as zones at risk of damage caused specifically by sea level rise by 2050. One observation is that areas at risk are typically surrounded by bodies of water. Our visualization of the greater Boston area depicts coastal areas as the first to be affected by sea level rise, which will result in devastating consequences to Boston's economy, property, and the lives of its residents. According to the NOAA Office of Coastal Management, the 2.8 million people living in coastal Massachusetts, most of which reside in Boston, earn a collective $206 billion per year. And all these areas could be at risk of flooding in the near future. The coast of Boston is vital to Boston's overall economy, and any permanent damage would result in devastating consequences for the city. In addition to evaluating risk defined by sea level rise, analyzing the MHHW, the mean height of the high water data, also provides us insight on the risk of flooding caused by sea level rise by 2050. To clarify, the NOAA defines MHHW as the average of the higher high water height of each tidal day observed over the national tidal datum epoch. This epoch would be equal to a uniform 19 years. Using this as a parameter for our models allows to estimate the most damage that can be caused by the highest point of water. Areas at risk of flooding are defined in green, while areas that will flood and be submerged are defined in blue. In the following visualization, it similarly depicts surrounding large bodies of water at risk of flooding caused by a rise in MHHW. Wetlands, specifically the Belle Isle Reservation and the Rooney Marsh Reservation, are the first to be flooded by the year 2050. The loss of marshes can cause dire consequences to the rest of the Boston metropolitan area. Marshes play a crucial role in natural storm drainage by absorbing and storing water, which reduces the risk of flooding in downstream areas. If these marshes are no longer able to store enough water due to the rise of sea levels, excess water will be displaced in surrounding areas and cause flooding and lasting damage. Apart from just the ArcGIS mapping software, we use Risk Factor, a highly regarded climate change risk detection software that deals with flooding risk. Risk Factor's moderate flood factor uses its own modeling to project a total of 4,994 residential properties, 620 roads, and 3,295 commercial properties at risk of moderate flooding, as well as 109 infrastructure facilities and 308 social facilities at risk of moderate flooding in the city of Boston alone. According to the same flood factor, there is a 26% chance of flooding over the course of the next 30 years for properties that meet the 100-year standard set by the city, with a year-to-year chance of flooding being 1%. As for properties that meet the 500-year flooding standard, the chance of flooding over a 30 period comes down to 6%, with a year-by-year chance of flooding coming down to 0.2%. These numbers explain a lot about the current situation regarding sea levels in Boston. Without the proper interventions and adaptations to alarming sea level rise and tide rise, the entirety of Boston will face lasting damage, much of which is irreversible. Many areas in Boston, including the Boston Airport and the Seaport, each worth over $1 billion respectively, will face some sort of lasting damage as a result of sea level rise.
Onto our recommendations, we decided to base them on some of the core factors causing flooding in the city of Boston. These include the overflow of the Charles River, the main body of water that flows through the city, and the cause of the vast majority of its floods due to lack of infrastructure to protect vulnerable riverbank areas, as referenced in the image on the right. According to our risk analysis 100 and 500-year sets, this is a problem set to only worsen as sea levels continue to rise. In addition, the excessive flooding of marshes near the city's coast leaves residents vulnerable to flash floods due to the lack of protection that these coastal wetlands receive. Our first solution to these problems involves elevating and protecting architecture. The elevation of architecture is a project that is already underway in the city of Boston through the Freeboard Elevation Project, in which citizens living in high-risk flood zones, as indicated on the map in dark purple, can elect to raise their properties by a minimum of 2 inches, which effectively removes them from floodplains, according to the Federal Emergency Management Agency, or FEMA. The natural protection of architecture also has its roots from Boston's East Boston vision, which seeks to create waterfront parks alongside the city's coastline to protect it from floods. The further installment of trees and vegetative barriers to absorb and slow the spread of water would protect nearby neighborhoods in the case of a flood. Our second solution involves protecting coastal wetlands from marsh flooding, which causes large-scale damage according to our risk analysis. This involved government sponsorship of the current project of the U.S. Army Corps of Engineers, or Corps for short, to acquire coastal wetlands near the Charles River for protection. So far, they have already managed to acquire 8,103 acres of wetlands, thus saving an estimated $17 million in potential damages. The government sponsorship of this effort to protect coastal wetlands would prevent further damages as sea levels continue to rise going into the 2050s. Our final solution is to increase the portion of Bostonians who have flood insurance. According to the Union of Concerned Scientists, a sea level increase of just a foot would leave 12,000 properties in the city at high risk of flooding, with an estimated collective property value of nearly $13 billion. Boston currently has a flood insurance policy covering up to $100,000 in a flood scenario, with an average premium price of $991. However, many people in flood risk zones do not have flood insurance. So government encouragement and incentives for citizens to purchase flood insurance plans would help decrease the risk of high flood damage costs for both the homeowner and the government. Thank you.